In this video, we're going to be looking at section 1.5, inverse functions. So a big thing to note is we're skipping 1.4 because we're basically going to do that stuff as we go. So here we go with 1.5, inverse functions. So suppose you've been given a function such as f of c equals 9/5 c plus 32. Its domain is degrees Celsius and range degrees Fahrenheit. So this is a function that you're going to put in a Celsius temperature and you're going to get out a Fahrenheit temperature from it. And we can even make a table with the values. We see that if we put negative 40 degrees Celsius in, we get negative 40 Fahrenheit out. 0 degrees Celsius becomes 32 Fahrenheit, 10 becomes 50, and 100 becomes 212. And so this is a good function. And this works really well if you want to convert Celsius to Fahrenheit. But what if you want to reverse this process? What if instead you want to convert Fahrenheit back to Celsius? Suppose you've got, for example, 150 degrees Fahrenheit. Well, what Celsius temperature is that? You don't want to just guess, keep plugging Celsius temperatures into that function and see what'll eventually get you 150. You could look at the graph and estimate, but instead what we want to do is we want to come up with a rule, a good function for getting back that temperature. That is, we want to come up with a way to reverse this process. So if we reverse this process correctly, we'll get a function whose input now is degrees Fahrenheit and which outputs Celsius. And so what we want to do is reverse this process. So we'll look, the Fahrenheit function, what it does, its first step is it takes C and it multiplies by 9/5, and the second thing it does is it adds 32. So if we want to reverse this process, we want a function C that takes in a Fahrenheit temperature and does everything in reverse. First, we want it to subtract 32, and then we want it to divide by 9/5. And so we've got here a function that does exactly that. It takes a Fahrenheit temperature and subtracts 32, and then instead of, dividing by 9/5 is the same as multiplying by 5/9, it just looks a little nicer. So this is the function that will convert back. And in this section we'll learn a little bit more about inverse functions, how to build them, and how to figure them out in a way that's better than going through all the verbal descriptions. So our technical definition here is we're going to say that a function g is the inverse function of the function f if f of g of x equals x for all x in the domain of g, and g of f of x equals x for all x in the domain of f. So the key here is that we're going to compose our functions and get back x, exactly what we started with. That is, we put in our input and we get our input back when we compose them in both directions. So let's go ahead and see an example of this. So we're going to show that these two functions we came up with before for converting Celsius and Fahrenheit temperatures really are inverses of each other. And just note that I've written them here pretty abstractly in terms of x's for their inputs just to ease our notation. So just like last section, what we do is to compose them, we start by putting the g function inside of this big f function. We then use that g as the input so that the 9/5 of the quantity plus 32 is coming right here from f. And now we're left with just algebra, so now we need to simplify. Things to note, of course, is that this 9/5 and this 5/9 when we multiply will cancel. So that what we're left with now is just this nice x minus 32 plus 32. Well, minus 32 and plus 32 are inverses, so we're just left with x. Now, this has gone really well, and you might be tempted to celebrate, but hold off, we're only halfway there. All we've done so far is we've checked off the first part. We've composed in one direction. We still need to compose in the other direction. We still need to take g of f of x and make sure we get x. Now we've gotten pretty good at composing things, therefore we can go a bit faster. So we can put f into the g function. We replace with what this means. We can see that the plus 32 and minus 32 will cancel. The 5/9 times 9/5 will cancel since they're inverses of each other, and we're left with x. Therefore, since both f of g of x equals x and g of x equals x, we have that they're going to be inverses of each other. Now you have to check these every single time, both compositions. I know it takes a little bit of work, it's some boring algebra, but we must do it. We must be careful. Some general properties to know. If you find the inverse, and if you find out that g is the inverse of f, well then we also say that f is the inverse of g. They undo each other. It's a very symmetric definition. Since inverses swap their inputs and outputs of each other, it's also a good idea to think about the fact that the domain of the inverse of a function is the range of f and vice versa. That is, your inverse function's domain was the range of the other function. We will look at this in an example later. And the last thing to keep in mind is that a function need not have an inverse, but if it does, it's going to be unique. If you and your friend are working on homework together and you say you have two different inverses for a function, somebody did something wrong, okay? There's only one right answer for these. Also, be very, very careful. Not all functions have inverses, but next we're going to talk about some ways to know whether or not a function will have an inverse. So one of the properties, and one of the ways to figure out if a function has an inverse, is that it has to satisfy what's called the reflection property. So this says that the graph of a function f contains the point AB if and only if the graph of the inverse contains the point BA. So the way to think about this was that we had 0, 32 was one pair of temperatures that was in the Celsius to Fahrenheit pair. Therefore, the inverse function needed to contain the pair of temperatures 0, 32 in Fahrenheit Celsius pair. And they have to be able to swap all of these pairs of numbers in your function. And this is a really nice graphical property to check on a function. So what I've graphed here is the function f of x equals x minus 2 cubed plus 1. And we want to see if this function has an inverse. And what the reflective property says, well, if it does have an inverse, what we need to be able to do is we need to be able to swap all of these inputs and their outputs. So if we look here on the graph, what we have is, here we have a point on our graph at 2, 1. And in order to have an inverse, we need to be able to go over to 1, 2 and draw a point as well. And that needs to be a point on the inverse function. Also, if we go to 3, 2, we need to also be able to go over to 2, 3. And this needs to be a point on our inverse. And at 1, 0, so this means 0, 1 needs to be a point on our inverse. And we could keep doing this for all the points. And what we'd have to do is we'd have to check that all of these points really are on our graph. And instead what we'll do is we'll have a computer do this much more quickly for us. And so remember that this was our original graph here in orange. And what we've done is we've swapped all of these points on our graph have now become points on the reflected graph. And because we're able to do this with all of our points, we're able to reflect, what we have is we have an inverse function. The other idea is that this red line here is just the line y equals x, and we can see that it's pretty symmetric. That is, if we folded our graph over the line y equals x, we'd get another graph. And since this black line, this black curve, is indeed a function, this means we do have an inverse. But the question, of course, is how do we find this inverse function? And we'll talk about that in a little bit. The quick way to tell if a function has an inverse or not is called the horizontal line test. It says a function has an inverse function if and only if every horizontal line intersects the graph of f at most once. A function has an inverse if and only if the function is 1 to 1. These amount to the same idea. So let's look at a picture and see how this works. So here we have a picture of some function that we'll call f, and we'll trace a few horizontal lines here. We'll see that every horizontal line I draw only hits the graph at most once, so we say that f passes the horizontal line test. That is, it's 1 to 1, so f has an inverse. And in a little bit we'll figure out how to go about finding that inverse. So let's see an example of a function that fails now. So here's a function, and I can actually tell you that this is just the graph of h of x equals x squared. So this function fails the horizontal line test. That is, we can throw a horizontal line here that hits the graph twice. Well, that's too much. Here's another one. Hits it twice. That's too much. And this function, it fails the horizontal line test because this function is not one-to-one. That is, if I take h of 2, I get 4, and also h of negative 2 also equals 4. So what I've got is I've got 2 points here that are going to be on the same horizontal line at 4, so this one fails the horizontal line test, no inverse function. So we have to be careful. We always want to check and make sure, of course, first that we have an inverse. So now the moment we've all been waiting for, we're going to go through how to find an inverse algebraically. That is, no more graphing, we're actually going to find the formula for it. So the first step before finding an inverse is to make sure it has an inverse, probably checking using the horizontal line test. So as an example, we're going to use this function we've been using all along, f of x equals x minus 2 cubed plus 1, and we checked this previously. We've already looked at the graph, and it has a pretty good, passes the horizontal line test, so it's good to go. So step 2 is where the real meat of this problem happens. So the first thing we want to do is we want to solve for x as a function of y. So the first thing we want to do is we want to write y is equal to our function, which equals x minus 2 cubed plus 1. And so just to make this look a little bit nicer, we'll remove the f of x before we do a bunch of algebra. But our basic goal here is just to solve as you've learned to solve ages ago in algebra class. We want to get x by itself, so we just have to undo everything around it. So we start by subtracting the 1 from both sides, trying to get that x by itself. And next we'll take the cube root of both sides. So taking the cube root removes the cube from the one side and makes a cube root of the other side. And only one step left, we just have to add 2 to both sides, and we've got x by itself. Now that we've got x all alone, we're ready for step 3. And step 3 says to interchange x and y. Basically what we want to do here is we want to take this fact that we had y minus 1 cubed plus 2, and we bring it down, and we swap out the x's for y's, and we write f inverse of x is equal to this expression. What we really want is people really like x to be the input to their function. They're used to it, so we give them what they want. We give them a function that has as an input that looks like an x, and here the inverse function. So now you may be very tempted to say, wow, it seems like we're done, but we're not quite there yet. There's 2 more steps we need to complete. We need to state that the domain of our inverse function is the range of our original function. So in this case, it's going to be all real numbers, because our original function, f, had range all real numbers. And the last step is the step that no one likes, but we all get to do it. So step 5, we need to verify that the composites equal x. That is, we need to actually check that they are inverses of each other. So this means you really need to substitute them into each other. F composed with f inverse of x. You go through all of the algebraic work, and hopefully you get down to x at the end. And of course you still need to check the other direction. I've just run out of room here. You need to check that f inverse of f of x equals x to make sure that it really works and you didn't make a mistake along the way. And you do need to do this every single time. Now it's time for everyone's favorite subject, trig. And in particular we're going to look at trig inverses. So we're going to start by looking at the function f of x equals sine of x. Now hopefully you're looking at the graph of sine of x and you're saying to yourself, Professor Williams, with all due respect, this function is not going to have an inverse. It fails the horizontal line test. I can take a horizontal line, draw it right through here, and I already hit 3 points. I'm not even looking at the whole graph and I hit 3 points. And I will say to you, you are correct. The function f of x equals sine of x does not have an inverse. So what we need to do is we need to be a little tricky so that we can make it have an inverse, or at least think about an inverse for this function. And so what we're going to do is we're going to not think about the entire function. Instead, what we're going to think about is we're going to think just about the function sine of x, but only with a domain that goes from negative pi over 2 up to pi over 2. So these are the red parts I've indicated here. And that way its range will only go from negative 1 to 1. And so if you look just at the red graph, this function is now 1-to-1. That is, if I attempt to put any horizontal line through this graph, well, that only hits once, that only hits once, that only hits once, that only hits once, that only hits once. That is, for the red part, this function now has an inverse. And what we're going to call the inverse of this function is we're going to call the inverse of this function arcsine of x. We are absolutely not going to write this thing right here. That is awful. That's bad notation. We are going to use arcsine to think about the inverse. Now, if you felt like it, you could go through and do the exact same thing we've done on the previous slide for every single trig function here. What you do is you go through and you decide on a smaller domain to use. You're not going to use the all real numbers. What you're going to do is you're going to say, well, I only want to use a part of it to make my inverse. So for sine, we're going to use just -1-to-1, which is going to give us, for our arcsine domain, and that will give us the range from -pi/2 to pi/2. Same thing with arccosine, arctangent, arccotangent, arcsecant, and arccosecant, every single trig function. And if you want, what you can do is look on page 42 of your textbook. It has a really nice picture of all of these graphs and all of their inverses. And instead of going through each of them one by one, instead what we're going to do is we're going to go through and see instead how to make use of these ideas. Now, one of the big things to remember here is that what you want to do is you want to think of y in terms of radians. Okay? The input to a trig function is an angle, and x is a ratio. Okay? So y will always be measured in radians, never degrees. And the output value, x, you get is think of as a ratio. You really want to think in terms of triangles, or if you learn trig on a circle, that's fine too. But radians, radians, radians. So this means that the output of an arcsine, arccosine, arctrig function is also in radians. So let's suppose we decided that we want to compute arcsine of sine of pi, a very reasonable thing to calculate. And what we could do is we could think pretty quickly. We could think, well, arcsine and sine are just inverses, so maybe this should just equal pi. Well, the problem is it's not that simple. You see, the issue is that in the arcsine function, you can't get pi out of that function. The range of the arcsine function specified up here is -pi/2 to pi/2. So instead we have to be a little more clever, think through this a little bit more. So instead what we say is we say, well, let's compute arcsine of sine of pi. Well, I know that sine of pi is simply going to be 0. I remember this from trig. And now I want to think, well, what angle that is in this range, that is between -pi/2 and pi/2, would give me 0. That is, I want to answer the question, when is sine of theta going to equal 0? So this means that theta has to equal 0. This is the angle between -pi/2 and pi/2 that will give me 0. Let's look at another example of this problem. So what we want to look at here is we want to consider another example, and this time we're going to look at arccosine of cosine of 2 pi. So the first thing we want to do is we want to calculate cosine of 2 pi. And when we do this, what we're left with is the arccosine. And if we forget, maybe we can always go look at the graph. We're following the graph over to 2 pi, and we see that at 2 pi, cosine is equal to 1. So we have a value of 1 here. And now we need to figure out arccosine of 1. So if we look at our function here, arccosine says that we need the domain to be between -1 and 1, and our range will be numbers between 0 and pi. So if we put any number in between -1 and 1, we'll get a number out between 0 and pi. So now what we do is we go over to our graph and we think to ourselves, well, This means that arc cosine will only take values where x is going to be between the values of -1 and 1, and we're going to get values between 0 and pi. So we look at our graph and we think, well, we have a value of 1 up here when we get 0. So this means that arc cosine of 1 is going to be equal to 0. Another way to think about this is that what arc cosine of 1, it's really a question that is asking, well, what angle theta gives cosine of theta is equal to 1, where what we want is we need our angle theta to be between 0 and pi. And in this case, the angle that gives 1 that's between 0 and pi happens to be that theta has to equal 0. So again, these can be a little bit difficult, but always remember that these inverse trig functions are really trying to trick you. Is that arc cosine tells you that the range needs to be a number between 0 and pi. So even though we started with 2 pi in there, we have to get something between 0 and pi out. So our last example here is going to be how to unpack this difficult looking expression, cosine of arcsine of 5/13. So the first thing we want to remember when we look at this problem is that arcsine and all inverse trig functions really are really just angles in disguise. So what this is telling us is that if we think about it, that sine of some angle is going to be equal to 5/13. And hopefully you remember back in trig that sine of an angle is the ratio of the opposite side of a right triangle to the hypotenuse. So what we can do is we can draw ourselves a right triangle, angle theta, opposite side, hypotenuse, and adjacent side. And what we have from this is that sine of this angle happens to equal 5/13. So this means that our opposite side has length 5 and our hypotenuse has to have length 13. Hopefully you also remember from the Pythagorean theorem that if we take the adjacent side and square it, add it to the opposite side squared, we will get the hypotenuse squared. So in our case what we have is we have the a that we don't know squared plus 5 squared equals 13 squared, and if we go through and solve this, we'll end up with an a equal to 12. So now we've completed our right triangle, and you're probably asking yourself, well, that's great, we've got a triangle, but what does this do for us? Well, let's go back to our original problem. We wanted to find cosine of arc sine of 5/13. And what we're able to say is that in terms of this triangle, this is the same as cosine of this angle we've called theta. And so if we look at our triangle here, and we remember that cosine is going to just be the adjacent side divided by the hypotenuse side, a nice ratio. And now we know exactly what those numbers are. So overall we can figure out this somewhat confusing looking quantity by just looking at a few steps. So just to review, the first thing is to always remember that trig functions give out angles. Using those angles we can build triangles. Using the Pythagorean theorem we can figure out the other sides, and then we can put it all together here to figure out the final ratio that we get, because cosine gives out a ratio. So for tomorrow you should work on your in-class problems, put a question on Blackboard, and let me know if you have any questions. Have a good night.